Good morning, everyone. Glad to be here. I gave a talk last year in the joint ASSCT meeting where I talked about the effect that row spacing has on plant available water. And today I'd like to kind of give a kind of update of where we've gone from here. But first I'll give a little bit of a recap of the results from that before I go on to some new results. So one of the things we did is this is some work that Dr. Paul White started in 2017. He did from 2017 to 2020, where looked at what was the effect of row spacing. So between 2.4 meter rows and 1.8 meter rows, which is basically 8 foot and 6 foot row spacing. And so that's measuring the total water content in the top 45 centimeters. And one of the things we found, this graph just shows let me put this up. Ooh, where is it? Sorry. Okay, so right here, this is just showing the amount of available water that's in the top 45 centimeters. And one thing we found that the 8 foot rows had more water available than the 6 feet rows, but yield wasn't different. And so we kind of wonder, well, what was was there any benefit to having more water? And so that's what got me thinking, and so I was looking, well, wait a minute, is there, basically from 2017 to 2020, it looked like there was high water availability for that entire nearly 4 years, which is kind of surprising. There's not too many places in the country that can say they had high water availability in their field always throughout, basically never having a period, even during dry periods where water wasn't available. And so I wanted to see what the effect that would have on look at plant growth. And so I want to look at it just like a top level approach, just to look at total photosynthesis over the field, and we can measure that using eddy covariance. This is also from one of Dr. Paul White's towers, where we can use eddy covariance to measure the gross primary productivity, which is here on which is basically the total photosynthesis that's taking place in the sugarcane field. And then on the x-axis is the evapotranspiration, so all the water that's being lost. So we can look at that relationship between water loss versus how much growth is taking place. And this is the colors of the dots represent different years. And you can see these lines, where the slope of these lines is the we call water use efficiency. So that's the intrinsic relationship between photosynthesis and water loss. And there wasn't too much. There's a little bit of difference in 2019, but for the most part, they're relatively consistent across years, which means that even though precipitation changes across years, the growth was relatively similar, which I was pretty surprised by. So I compared the amount of GPP, or photosynthesis, and compare that to the available water, and I found no relationship. Meaning that GPP is not dependent on plant available water. Like I said, there's not too many places that can say that. And that was kind of interesting. I come from a background of where we look at where water limitation's a problem, where you look at and I was kind of surprised. Even the upper Midwest, where they don't irrigate either, they're still water limited, and if they did irrigate, they would see an increase in yield. So I started thinking about that from the perspective of water, or is there something we can take advantage of? Is water something we can actually help us to increase yield? And the reason why I'm thinking about that is based on this relationship. Here on the x-axis is stomatic conductance, and you can think of stomatic conductance as flow of water out of the plant. So that's water loss. On the y-axis here is the photosynthetic rate, and you can see there's actually a strong relationship between water loss from the plant and how much that plant's photosynthesizing. Actually, that relationship, water loss is the best predictor of growth that we have. There's no relationship between any nutrient and growth that's as strong as water loss. And so I thought, well, so basically meaning you increase the amount of water going through the plant, you're going to increase growth. That relationship you cannot break. And so I started thinking, well, is there ways that we can do that, to actually be able to take advantage of more water, of the high water abundance that we have here? And one way is actually breeding for, or selected for, insensitive stomates. Stomates, of course, are the pores in the leaf, and they open up, and the reason why you can do this is you can see this cross-section here of a leaf, where those stomates open up to take in CO2 that's assimilated in photosynthesis, and at the same time, as a consequence of those stomates being open, they lose water. Well, if the stomates are insensitive, meaning that they are slow to close, they remain mostly open, we're going to lose more water, of course, from the plant, but there also increased amount of CO2 being taken up, which means more photosynthesis, and especially if that's coupled with greater photosynthetic capacity, which is the ability to do photosynthesis. We might be able to actually see increases in photosynthesis and growth. But one of the questions, of course, is there actually variability in these traits in sugarcane? And so that's what one of the things I've been doing this year is we did a survey of different sugarcane varieties to see if there is actually variability in the amount of transpiration and photosynthesis taking place. And so we surveyed 60 different varieties, doing measured photosynthesis, or what we call gas exchange, which is the this movement of water out of the plant and CO2 into the plant, from about 5 to 15 plants per variety. See how variable the trait is, and also see how much variation is between varieties. And then we also measure different canopy architecture traits. See, because one of the things that's really important when you look at physiological traits is how this trait changes across scales. We look at it, we can look at it from the subleaf level, so the molecular level, and then compare that to the leaf level, then the whole canopy, and then a whole field. And it's really important to look at these across fields, across these different scales, these traits. And so we also looked at different canopy architecture to see how that would affect this trait. A lot of this we're still doing, but we have leaf area, and so I'll show you what we found with that. And then also different stalk traits. So first, we want to know if there's how much variation do we find, and this is this graph figure just shows right here along the x-axis. This is just all the different varieties, and they're just rank ordered from the smallest to the largest. And we see in photosynthetic rate there's actually is quite a substantial amount of variation among these varieties, and these are actually highly selected varieties already. They're already quite far advanced in the breeding program, most of the varieties, and so it's. I was pretty surprised that there was quite as much variation as there was. And then also with stomatal conductance, we saw the same thing where there's quite a bit of variation in stomatal conductance. So then I plotted those, one against photosynthetic rate on the y-axis and stomatal conductance on the x-axis, and you compare these two traits so you can see that relationship between photosynthesis and water loss. And these lines, these are this vertical line represents the mean stomatal conductance, and the horizontal line represents the mean photosynthetic rate. And so you can see kind of where the different varieties fall relative to each other as far as relative to the mean. And a couple things that I found that were pretty interesting is that the commercial varieties, and there was about 10 commercially released varieties in here, most of them are kind of hovering around the mean. They weren't necessarily, I was kind of surprised by that. I was expecting to be maybe a little higher in the photosynthesis, but they weren't. They were all about the mean. Except for A85, it had pretty high photosynthetic rates, but average stomatal conductance, which typically when you have a high photosynthetic rate, but yet it's not opening its stomates more, that's an example of higher photosynthetic capacity. It means that the machinery within the plant is actually working better. And so we're actually looking further into A85 to see if that is actually the case. Why is it have a higher photosynthetic capacity? If that's enzyme activity or what's going on there. Another thing that was interesting is this one right here, and we're still looking at this one, and this was multiple leaves, so this is a very consistent value. That's not just a one strange plant. But this is L17 428, and it's just screaming, both in photosynthetic rate and also in stomatal conductance. And so we're looking further into that. Why, why does it have high values? Are we looking at that one where we have higher photosynthetic rate or higher photosynthetic capacity and also higher substrate availability? It's opening up the stomates, taking up more CO2, and taking advantage of that. And so that's one that's interesting, because that's something that particularly, I think we would actually want a trait that what we would like to see. Now, when we compare that then to canopy traits, one thing I just want to show here, some of the different canopies. Is, you work with sugarcane. One thing you notice is the canopies don't look the same. Look at the leaves; they're not the same between varieties. And some of them are kind of small canopy, very erect leaves. And you have some, like for instance, on the other side here, very large canopies, a lot of leaves, high leaf area, and so. That could, potentially that could really change how much photosynthesis is taking place. You have a large canopy, even if you had relatively low photosynthetic rates, if you look over the entire plant, it could actually be quite high on the plant level. So now what we found is that, yeah, indeed, we found that there was that interaction. So this right here, this graph right here, on the right is at the canopy level, photosynthetic rates and transpiration rates. And there's a couple things I want to point out. One is you see the relationship really tightened up, and that's typical that these relationships, once you bring it to the whole plant level, there's interactions with leaf and whole plant hydraulics that really limit how that relationship plays out. But I'd just like to point out a couple things here that was interesting. You see this one of the varieties on the 20 series here is HOCP 20541. It was down here, is a little bit above average photosynthetic rate. But once you take it into account the leaf canopy structure, you can see that it's now actually has relatively high, so the potential photosynthetic rate is really high. Another thing I'd point out, of course, is that 428 still way at the top, so we're definitely going to be looking at that one more. But another thing that was interesting too, and I still a little puzzled by this, I'm kind of surprised, is that a lot of the commercial varieties were here down at the bottom. They had low canopy photosynthetic rates and also low transpiration rates, so we're going to have to look at why is that? Why is that there's this that there seem to be congregating there at the low end of this relationship? So yeah, we'll have to do more, of course, with trying to figure that out, why that is. But also, I'd like to, one thing is some of the steps we're still working on right now, but I'd like to show is, what is the effect that the canopy has on different stock traits? And I was curious, is there any relationship? And we found that there was, and it was actually, basically, if you look at cane weight versus on the y-axis and the x-axis canopy leaf area, that there's a pretty good relationship. I mean, it's a R squared of 0.51 for basically bigger cane, heavier cane has more leaves. So now we're looking at, okay, we can look at that way, but now we need to look at, okay, how does that translate out to a field level? Because if you have, for instance, varieties that have maybe they're not really big cane, but they have a high population, therefore each photosynthesis on the per plant level, per stock level might be very high, but because there's such a high population, it can you look at photosynthesis over the entire field, it might actually be very high. And so now that's what we're doing. We're going to be doing later is once we get that data from James. Todd, we intend to look at his population counts and stuff. We can start to look at and see how this then we can scale up to the photosynthesis up to the plot level and see how this relationship plays out at the plot level, at the field level. And also we start looking at, okay, now if you have different erectness of leaves, how that affects how much photosynthesis takes place and how much water is lost. And so, but we're definitely encouraged by the relationship what we've been able to find, that there's quite a bit of variation to work with. And I just like to, in conclusion, just come to some of the conclusions. Is one that the water availability does not control cane growth, and we're going to work on this more to see how some of the early season, like last year, it was pretty dry early on, and I did some watering a couple plotches to see if I'd get a response. And I certainly did get a response in growth, and so we're going to be looking at some of that to see if some of these how that affects, especially the early season water, how that affects growth. But it doesn't look like it's a big player, as which is surprising. Like I say, this is one of the few places in the United States that can that's actually the case. Also, I'm encouraged we found substantial variation in gas exchange and canopy traits, and so that's something we can work with. The idea is if we can find more of traits that are important for sugarcane that actually influence sugarcane yield. We can start to we can actually start selecting for those, so that can be part of the selection process of sugarcane. So that's the goal, and the hope is that we can use these, actually look at traits that will influence later varieties. And that's the case that we're finding these traits at the leaf level and the subleaf level is actually affecting, and we've seen the effect of them on the cane level. And so, and we'll continue this work and see if at the plot level as well. But just in ending, I'd like to acknowledge thanks for Dr. James Todd for providing the varieties for this analysis, and my lab tech that's been working for the last 6 months trying to get all this stuff processed, and right now on his computer still processing. But I'd like to say thank you for everyone. If there's any questions. What age? This was, I took the measurements in July, so it was in the peak of growth in July and into August. So these are, peak grand growth. Yes. It's a Lycor 6800. Is one we use. Excuse me? What temperature I was measuring at? This was, we're doing this for the gas exchange measurements. I believe I was measuring at, I think we're doing, if it was, I think 31 degrees Celsius is the temperature we were at, 30 or 31. And yes, it does make a difference. So that's another thing put into is it can change. It's definitely photosynthetic rates, temperature dependent. Huh? Oh yes, yeah. So it does affect. It'll affect photosynthesis because that affects enzyme activity, and it affects stomatal conductance because it'll affect the temperature will affect the vapor pressure deficit. So it'll affect how much, not as much stomatal conductance. That's why we use it a lot when it comes to looking at as a measure for. It affects more transpiration rate, not as much stomatal conductance, and that's why we use it actually as a potential for selecting. We use stomatal conductance is less affected by environmental conditions. Not that it's completely unaffected, but it's much less than transpiration rate. Yes. So that is, so you're asking what measurement time, how that right now is something we're working on. Is it is a slow process. We were making measurements because you can't have it out in the rain and stuff. We're actually making measurements in the lab, and we're taking measurements at physiological steady state, And it's a slower process. They're much more consistent. So that becomes, you get values that are, I mean, you can pretty much, when you get that value, you can pretty much guarantee the next plant of that variety will be at the same value. However, it is a slow process, and we're working on that. So some plants, because what happens is you put the plant in there, in the chamber, the leaf, and it takes time to wake up. It takes time to get back to get to that steady state. And for some varieties, it could be, you know, an hour and a half of waiting. So that is an issue that we're working on, is how can we speed this up? So if we're going to use this for lots of varieties, how can we speed up that process? Yeah. Yeah, in the field it's not as bad. If you're in conditions where you can, they're in, you don't have to change anything, it's a lot quicker. It'll be like 20 or 30 minutes, but still, yeah, we need to get that faster.